Hello and welcome back to Calculus 1 section 3.2 on the derivative as a function. Now, in the last lecture, we have seen that function you get from the calculation for the slope of the tangent line was called the derivative, and it was the function that would generate or calculate all of the tangent line slopes as you plug in whatever x you are interested in and the input. So we started by saying that m tangent was equal to the limit h goes to 0 of f of x plus h minus f of x divided by h, and then we said that that's the derivative because it gives us a function, not a point. And I'll just say m tangent over here at x equals a. So it doesn't give you particular tangent, it gives you all of the tangents, right? And we say, okay, great, so it's a function. Now it's really interesting to understand here that you're finally getting this in this place with calculus where the true nature of the calculus is revealed. You change the function. Calculus operates and changes functions. Where prior to that, when you studied everything to algebra through pre-calc and stats and so on, functions were changing numbers, right? So we start by relationship, understanding the relationship between the two. We know how to compute. Maybe we can do another example just to reinforce. Let's compute. Find the derivative for, let's go, f of x equals square root of x minus 3. This is a problem calculating limit. I mean, this problem is a fair game for the first test even. I just don't use the word, right? I just give you the problem, this one, right? It's the same, I mean, you actually do have these problems, and I mentioned that in the homework for 2.3. You have this problem to solve. It was just the words, derivative, right, and rate of change and stuff like that. That was not present, but 100% of calculation was there. So the problems that I did in the previous example, all of them are fair game for the exam because it's just calculating limits. Now the concept, right, since we are not going to have chapter 3 on the test, the concept and asking you concepts from that would not be a fair game because we agreed to have exam on chapters 1 and 2. So whatever I'm going to do now is still chapter 2. We're going to do the limit. H goes to 0. Now we're going to have f of x plus h, and then minus f of x divided by h. This is now 2.3 problem to solve. And we do that by rationalizing. So it's going to be x plus h minus 3 plus root x minus 3 divided by square root of x plus h minus 3 plus square root of x minus 3. And the limit h goes to 0 is, on top you have difference of squares, so it becomes x plus 3 minus 3 minus x minus 3. And in denominator we're not going to multiply, we're going to leave it as is. That's experience. If you multiply, then it's going to be harder later. I mean, you would have to factor in all of that stuff. On top, I have minus 3 plus 3 is gone, and x minus x is gone. So what I actually have is the limit of h divided by age times this parenthesis. This is where age cancels. And you are left with the limit age goes to 0 of 1 over square root of x plus age minus 3 plus square root of x minus 3. And that is 1 over 2 square root of x minus 3, because that age goes to 0, and you just have two square roots that are the same, which you can add together. So apple plus apple is 2 apples, and you have your you have the answer. So the function f of x equals square root of x minus 3 has the derivative of 1 over 2 square root of x minus 3. So that's the function, and that's the derivative. All right. Just going to point out notation real quick before we jump into the content of the lecture. Make sure that you are not writing that the function is equal to the derivative, because it's not. That's the same as writing 3 is equal to 7, right? 3 is not equal to 7, and the function is not equal to the derivative. There is one case, but that's a special case. We'll discuss that later. But in general, function is not equal to the derivative, and you are not allowed in the notation to write that. So you cannot say, square root of x minus 3 is equal to 1 over. No. They are two separate worlds. They have separate graphs, separate properties, separate, everything separate. So we have to be careful with the notation regarding that. All right. Now, what we see here is that this is the function given to us, and then we have a function which is the derivative. So in some sense, you put the function into this machine called the derivative, and out comes the different function, right? That's the thing that's happening here. Since both are functions, they both have graphs. And our hope is that those graphs are somehow related, so that we can make some conclusions, right? Looking one at the other and connect them in some way. And actually we can. It's really cool. So I'm going to go here with the basic function and its derivative. So I'm going to say f of x equals x squared, and then the f prime of x is 2x. Now in between, obviously, there is that process of the limit. Let's put it here. Limit goes here. So those of you, obviously, that care and actually study by going through notes and concepts first, you will fill in that, right? You will say, okay, let me do this on the side real quick and verify. So now I have two graphs. I have a graph for x squared, and I have a graph for 2x. And when you draw them separately like this, they don't really say much. This is your f of x, and this is your f prime of x. So they don't say much when you have them like this. But if you draw one over the other, some things immediately start becoming clear. So now I'm going to draw this again in black. We have our x squared original function. I can call it f of x. And in red, we have our derivative. when you look at this graph, there are two connections that can be made immediately. So one of them is when function is decreasing, derivative is negative. So we can see over here function decreasing, meaning going down, and you see that all of the values for the red function are negative y values. Flip side, when f of x is increasing, derivative is positive. So you can see it being over here, increasing, and you can see all of the red y values for the red line, right, are positive numbers. There is one more feature which I'm going to add later, but it's not the best example to explain that feature, so I'm going to move to the next example and then I'm just going to point it out here. So far we have decrease is negative derivative and increase on the function is a positive derivative. Let's jump to the next example to see this other feature that I mentioned. So if I have some arbitrary function f doing stuff like that, and that's my function f of x, I'm going to pick the maximum and the minimum of there we go. And now, because maximum and minimum are where the increase changes to decrease and decrease changes to increase, right? So that's why I'm getting those min and max points. So we said if the function is increasing, the derivative is positive. If the function is decreasing, derivative is negative. And then if the function is increasing, the derivative is positive. So I'm able to sketch a graph of the derivative by looking at the function. I can say, okay, I have increase here, so the derivative is increasing, and I have a decrease in the middle, so the derivative is negative, has to be below x-axis. So I put a little belly over there, and then f of x goes up, again positive, and so on. What do I have overall? What do I have overall here? Well, those are the rules we know from before. Nothing new there. Well, if you paid attention, when I started this, I said this. So that gives us another one, and that's actually a very important one. So so the minimum and maximum values, right, min and max of the original function, of the min and max of f of x gives zeros of the derivative. And now you're gonna maybe say, yeah, whatever. Oh, not whatever. That concept is insanely important. let me give you a simple physics experiment. Please grab anything laying around you and throw it up. Obviously, it will come down, right? And you will hopefully catch it. So throw anything up in the air. And it's important, guys. I'm not just saying, okay, whatever. I'm actually want you to do it. Pick any object laying around you, throw it up and observe what happens. Look at the object. The object is going to go up, stop, and come back. It stopped at the maximum height. Stopped at the maximum height and came back down. When the object stops, what's its speed? What's its velocity? Right? It's 0 miles. Exactly. Very good. It's 0. So when you throw something in the air, it reaches its maximum height. Height is distance going up. When it reaches the maximum distance, it stops and it goes down. Now, did we say that velocity or speed was change in distance over change in time? So you can see that the velocity equals 0, right? Gives you the distance over time. So it was the speed, right, that came to 0. And you see that maximum height, which is the maximum height on the picture, right? If you throw something up, it's going to go up and then come down. If you shoot it at the angle, it's going to go up and down. But your vertical velocity went to maximum velocity and then dropped to 0 when you get to the maximum height. The trick is that the gravity is slowing down the object you throw. So you throw something up. Let's go back to this one. You throw something up at some velocity v0. It will be constantly slowing down because the gravity is pulling the other way. When it reaches the maximum point here, velocity equals to 0 and y equals to max. And then it's going to go down, reaching y equals 0, velocity equal to max, because it hits the floor or falls into your hand with the maximum velocity for the height it's at. Because going down, and we'll do those equations later in the course, it kept accelerating because it's changing the speed, because the gravity is accelerating the object going down. So, getting a free lecture on kinematics. Guys, that's what calculus is. This is how you explain the world, right? And kinematics is the motion, right? Is changing in change of distance in time. Hold on. There we go. Much better. Now, we have three of these points now. And let's have another one for 1 over x. So if you have your f over x to be 1 over x, then its derivative f prime of x will be negative 1 over x squared. And you go, how do you know that? It came to me in a dream, okay? For you, you are going to go and you are going to compute because you're going to use the limit thing, right? And you're going to get this answer. Now, I did have earlier 6 over x, and the answer worked out to be negative 6 over x squared, so that should give you a hint, right? But let's just go with the idea that I am infinitely wise and just know it. Or, no, I said it came to me in a dream. It's the same thing. Anyway, so if I am to draw these two functions, on separate graphs, I don't really get a lot of input. But if I draw these two graphs on the same one, we have some input. And we can find one more thing. Now, first of all, 1 over x has this vertical asymptote here. And when you draw 1 over x, you get this. So the black is 1 over x. Now the red one is going to be this. And that's your negative 1 over x squared, the derivative. Maybe I should put the derivative in red, let's see better. The derivative and the black here, f of x. There we go. We don't have min and max on the black function now, so we're not going to have the derivative touch 0 anywhere. It's not going to cross x-axis. Do we all see that rule? That was a rule 3, right? If the black function, the original function, so if the black function has min or a max, the red function must have 0 crossing the x-axis at some point x, at the point where the maximum was. That was the point of the previous, right? So at this point A over here, right? The black function has a maximum, the red function goes through x-axis, creating what we call a 0. Same thing at the B location. Black function has a minimum, red function, which is the derivative, it is going through 0. Now, when you look at this example, black function does not have min or a max, which means that the red function will not go through 0. And it doesn't. All other features are kept. Rule number 1, increasing function gives the positive values, and rule number 2, decreasing function gives the negative values. That's all preserved. You see, this is decreasing, it's negative. This is also decreasing, and it's negative. So we're good. So you can say a lot about a function without knowing what the function is. And when you take a look at the stock market graphs, which show you the way the stock looks across the different times of a day, right? They give you the graph like this, and it goes like this, right? And then it closes at 4, and this is at 9 a.m., closes at 4 p.m., and it closes here. This is actually, it's a bad graph because I want more. Okay, let's go. And closes. I guess they all look like this because they induce heart attack, right? Looks like a EKG reading. Anyway, this is money of what the stock is worth, right? In case of Apple, like $100 something. In case of Amazon, $3,500 per stock. I don't know what. Let me just see how far Amazon is. Amazon stock. Ooh, it dropped down. It dropped down to $2,955. Yeah. So one Amazon stock now is $2,955. I mean, $54.91. Who cares? 9 cents. I mean, you do care if you have 100,000 shares times, right? 9 cents is thousands of dollars, but yeah. So if you have 1,000 shares, you have $3 million on 1,000 shares for Amazon at this number. the other day, their stock was at 3,200 almost. Yeah, 3,184 looks like was the largest. 3,184. Interested in what happened. They dropped. Anyway, do you really want to look at the whole thing, right? Or you just want to have a line that goes through like that and say, yep, losing money, right? Losing money. This doesn't have to be any particular stock. It's just, the concept of mathematics. So instead of looking at each value, you hit it with a single line, and that line has a negative slope, meaning losing money. Negative slope means decrease, right? So this line has a negative slope, and the negative slope means decrease. Now, in the example of stocks, means losing money. If that line was going this way, then that's a positive slope, and then it's gaining money. So these are the concepts that you can literally time. I mean, I talked a lot about kinematics, right? And I talked a lot about the physics in general. But here is the example, right? Business economics, money, all of that stuff has finance, right? All of that stuff uses these concepts as well. Now, looking at the situation here, you also have situation where you have no derivative, and you have, how limit does not exist. There are cases where derivative does not exist, and the best candidate to understand that is clearly the candidate called absolute value function for x. So consider f of x equal absolute x. Now, the definition for this function is x for all x is bigger or equal than 0, and negative x for all x is less than 0. And its graph, the black graph here, is a 45-degree line this way, 45-degree line this way, and we're done. Right, that's that. Now, if you are to find the derivative for this function, derivative of x is 1, and derivative of x, negative x is negative 1. So now, the derivative is constant. Well, duh, right? If your function is a linear line, and you're looking for the derivative, which is the slope of the line, what the slope of the line you have is the derivative. So, let's say this is where 1 is. You have your derivative to be there. On the other side, you have your derivative to be here. That's the same function. It is a function. It's called step function. So now the black function, the absolute value of x, so the black function is continuous f of x function. The red function is a discontinuous step function. The problem has the derivative everywhere except at 0. Why? Well, remember the limit? Limit said what? What did the limit say? Limit said that limit from the left and limit from the right has to be the same. What if I look for the limit x approaches a, which is x approaches 0, before we switch to age business, right? And I had my f of a plus h minus f of a over h, that old formula. Well, when I approach the limit from one side, I'm gaining a negative 1. When I approach the limit from the right, I get positive 1. The limit does not exist, but limit defines the derivative, Therefore, derivative doesn't exist at that point. So you have to be careful about these things popping up in existence. And we're going to say here, write it in blood, limit does not exist at x equals 0. It exists everywhere else. We can also say function is not differentiable at 0. That's another way. Or f of x equal absolute x is not differentiable at x equals 0. That's another way to say the same thing. The word differentiable means able to take the derivative, right? Or taking the derivative. So you say differentiate function. That means take the derivative. So the word differentiable means able, in this case, in this context, means able to take the derivative. So you are able to take the derivative at any point other than 0. Now, what do we have at 0? We have this spike at 0. You see that the sharp corner? And at that point, derivative wants to be -1 and +1 at the same time. And then can decide, right, which way to go. Right? So you have a situation where you can have a function that has no derivative at the point, has derivative in infinitely many points, but then there is one particular point where it doesn't have. Also happens in situations when you have vertical tangency, it's not differentiable at the point, and all of that stuff. And because of that, we can now go back here at this example and fill in, now that we understand what it means it's not differentiable. We will say the rule number 4, this one can be, I guess, blue. Rule number 4 says that if f of x has VA at x equals a, then f prime of x has VA at the same point. In some sense, location of the vertical asymptote is preserved. You cannot have a vertical asymptote in, in function at 2 and then derivative at 5. No. If the function has the vertical asymptote at 2, your derivative will have the vertical asymptote at 2. And that's what the blue rule number 4 is for. And and then derivative doesn't exist at that line, which was the story we had below as well. So now, by the way, that's the lecture. I hope you're not disappointed. To put all of this together, right, in one concept, we say it this way. Your function, which is always the one that I drew in black, will govern a lot of things about the derivative. When the function is decreasing, the derivative is negative. When the function is increasing, the derivative is positive. Min and max of the function will make derivative equal to 0. And at the end, you have that the vertical asymptote, right? If the original function has the vertical asymptote, the derivative will have the vertical asymptote at the same point. So now, homework, exams, labs can ask you to sketch the graph of a derivative given function, or to sketch the function given the derivative. And those are the favorite ones, obviously, for labs, exams, and so on, because you have to think backwards, right? And really show the mastery of the content. And those are actually the ones that are very important, because many times in nature, as a scientist, or engineer, you can observe and measure the change, which is the derivative, and then figure out what is the concept, i.e. equation and a function, which gives that kind of output. And that's the kind of thinking that we need to develop, right? So you go and you say, so okay, this is how the speed is changing, the speed of the wind, the speed of the current in the ocean or something. You can calculate, you can measure that, and then once you have the graph for it, you say, oh, okay, so now this is supposed to be which we'll later on call potential function, which generates the field you just measured. I mean, the details of all of this stuff will be in Calculus 3, but you start everything right now. I mean, understanding the connections between derivatives and functions. And that's 3.2, way shorter, obviously, than 3 times shorter than the previous lecture. I will see you next time.